the day of reaching the destination. Just obeying an inner decision, embarking on the journey. A precise, comprehensive, and people-benefiting solution for in vitro diagnostics serving the public health. Every inch gleams, condenses into the pulsating ideal. With a determined heart, courage emerges from past steps. Knowledge in motion, only focused on steadfast progress. The compact immune quantification analyzer initiates the self-developed era of Zybio. The eruption of creativity, a rigorous competition with details, a mad breakthrough to the limits. Here we conquer several core technologies. Gene engineering antigens, antibodies, diagnostic nanomaterials, various signal amplifications, rapid nucleic acid extraction and PCR tests. Here, we collide sparks of wisdom, turning each conception into reality, launching a fully independent intellectual property TLA, and automated sample processing system EXLab. Here, we break free from fixed thinking, analyzing the concrete, perceiving innovation, understanding usage habits, anticipating customer needs. Cold modes convey delicate care, lean management in every product detail. Light is not just a bright beam, it is the carrier of energy. Comprehensive is not merely all-encompassing, it empowers precision. The 9+1 product line, encompassing clinical chemistry, clear, POCT, coagulation, hematology, urinalysis, mass spectrometry, molecular, pathology, paired with intelligent laboratory management system, efficiently providing laboratory solutions worldwide. Research centers scattered across the country, connecting Zybio's intelligent network, breaking the technical barriers set by the industry, pulling together the entire industrial chain from raw materials to core components. Establishing the Zybio Technology Park, creating an integrated space for raw material development, research and design, and product manufacturing. Customer service covers full-time, online and offline. We integrate our thorough philosophy into every corner, fundamentally providing integrated, traceable products and thoughtful services. Dedication to accuracy. In the future, belonging to every sincere practitioner, interpreting the endless charm of the in vitro diagnostic industry with innovation, serving the public health with high-quality diagnostic solutions, promoting economic development and technological advancement in the industry. Light, carrying ideals, gathering energy, we, chasing the light, will ultimately become the light.
Ladies and gentlemen, a very warm welcome to the third session of the DiagHub series. Today, we turn our spotlight to point-of-care testing, a field that is revolutionizing how and where diagnostics happen. From emergency rooms to remote communities, POCT is breaking down barriers by bringing testing closer to the patient, enabling faster decisions, better outcomes, and ultimately more accessible care for all. This session highlights a growing frontier, the pursuit of diagnostic precision at the point of care, whether through cutting-edge biomarker research or advanced molecular tools. The goal remains the same: to support clinical decision-making with clarity and confidence, and to bring life-saving insights closer to the patient. At DiagHub, we believe that the true innovation emerges where science meets clinical need. Let us continue to bridge the gap and together shape the next chapter of diagnostics. Thank you for being part of this important conversation. Let's begin. Now I will introduce the moderator of this event first. It is my great honor to introduce Professor Carolina Gucho Espinoza, a highly respected clinical pathologist with a specialization in microbiology and immunology. She has a Doctor of Medicine in microbiology and currently serves as the head of clinical pathology at Dos de Mayo National Hospital in Peru. In addition to her clinical leadership, she is an associate professor at San Marcos University, where she is deeply committed to academic excellence in medical education. She also served as the president of organizing committee for the 2024 ALAPAC Annual International Congress, and is a frequent speaker at international scientific and medical conferences. She has published more than 15 peer-reviewed articles with a focus on infectious diseases and cervical cancer screening, contributing valuable insights to global public health. Her contributions during the pandemic earned her Peru's Outstanding Pandemic Service Medal in 2021, and she was also honored with the Teaching Excellence Award from San Marcos University for 2 consecutive years, 2021 and 2022. Please join me in warmly welcoming Professor Carolina Gucho Espinoza. Welcome.
Thank you for the gracious introduction, Ms. Celaya Wan. It is my privilege to participate in this gathering of the kind invitation of Zybio and to serve as a moderator today. Today, from the DiagHub platform, I'm thrilled to exchange knowledge with experts from across the globe. And I'm particularly excited to introduce our two excellent speakers, both from China. Their expertise and insights in laboratory medicine will certainly inspire us and bring new perspective to the way we think about clinical diagnostic. Their contributions are invaluable, and I'm looking forward to the ensuring discussion that would follow. Our first speaker is Professor Dr. Bo Situ from China. Please let me introduce him. Professor and Deputy Director, Nanfang Hospital, Southern Medical University, Youth Editorial Board Member of Interdisciplinary Medicine. Recipient of prestigious awards including the Yangtze River Scholar Mo and Guangdong Science and Technology Progress Award. Pioneering basic research and clinical translation of novel in vitro diagnostic technologies, example, extracellular vesicles. In the past 5 years, as the first author of corresponding author, 21 research papers have been published in top journals, such as Nature Communications, Advanced Materials, and led national key R&D projects. Recognized young leader bridging cutting-edge diagnostic and clinical application. Concurrently serving as a young editorial board member for the academic journal Interdisciplinary Medicine and a member of the Youth Committee of the Clinical Laboratory Medicine branch of the Chinese Medical Association. Next, we turn our attention in the cutting-edge field of bacterial extracellular vesicles. Please join me in welcoming Dr. Bo Situ, who will explore detection of bacterial extracellular vesicles and their clinical application. Let's give him a warm welcome.
Thank you, Dr. Carolina, for your warm introduction, and it's my great honor to be invited. And today I would like to introduce our research about the detection of bacterial extracellular vesicle and their clinical application. And I'm Bo Tu from the Department of Laboratory Medicine of Nanfang Hospital in Southern Medical University in China. And first of all, I would like to introduce extracellular vesicle. And extracellular vesicle are lipid bilayer vesicle that's secreted by all cells. And based on difference in their biogenesis, and extracellular vesicle, short for EV, can be classified into microvesicle, exosomes, and apoptotic bodies. And all of these vesicles have nanoscale diameters, and exosomes as one of the subtype of EV and carry molecules such as nucleic acid and proteins and lipid. And in addition to mammal cells and bacteria and other microorganisms can also secrete extracellular vesicles. These are known as, in bacteria, they are known as BEV. That means bacteria extracellular vesicle. We call them BEV. And BEV are also lipid bilayer vesicle contain cytoplasmic proteins, nucleic acids, and other molecules such as the peptidoglycans and virulence factors from their mother bacteria. And based on bacteria biogenesis, BEV can be divided into three types: outer membrane vesicles, which block from the outer membrane of gram-negative bacteria, and outer inner membrane vesicles, and explosive outer membrane vesicle released during gram-negative cell lysis and carrying both inner and outer membrane components, and cytoplasmic and membrane vesicle from budding cell death in gram-positive bacteria. And each biogenesis pathway produces BEV with unique cargo compositions and different biological function. And BEV have diverse ingredients, including lipids, proteins, and nucleic acid, and metabolites. The components will change in different physiological and pathological conditions. So the composition of BEV is important in understanding their function. In this molecule, they play vital roles in different process media by the EV. And due to the nanoscale lipid membrane vesicle structures carrying a large number of bacterial active ingredients and stable properties, and BEV can serve as important media of bacterial function, and they may participate in bacteria and host interactions. And recent studies have shown that BEV are closely associated with diverse disease such as sepsis, pneumonias, and diabetes, and then play a key role in the progression of this condition. And since they have different effect on disease, one major question is that how to this vesicle reach and affect the remote organs from humans and the tissue of the host. So to answer this question, BEV detection and tracking are of great value in understanding their distribution, concentration, and the mechanism. However, the BEV detection currently faces two major challenges. The one challenge is the lack of specific and universal BEV markers, and the second is the lack of a high precision detection platform. Because the BEV in biological samples are mixed with a large number of host cell derived EV. That means they are mixed with a large number of the mammal cell EV. So how to achieve specific labeling and highly sensitive detection of BEV is a big challenge. So based on the above background, we propose three major scientific issues: how to specifically separate and detection a BV in complex biological sample, and what's the distribution patterns of BV in human samples, such in the blood, and what is the application value of this BV from human sample in disease. And next, I will introduce our research work to solve this scientific issue above. We focus on BV biomarker discovery and development of detection platform to explore the potential and BV in disease diagnosis and for disease treatment. To determine whether gut bacteria secrete BV into the circulation, we first engineer fluorescent E. coli super resolution image, confirm that the BV secreted by the fluorescent bacteria in the mice was similarly labeled with the fluorescent. And after the fluorescent E. coli was colonized in the mouse intestine, we isolate mouse serum EV and found that the fluorescent BV can be detected in the mouse circulation. This result indicates that the gut bacteria can release the bacteria extracellular vesicle into the bloodstream. And flow nanoanalyzer is a platform that could achieve single particle detection, even the size down to the 14 to 1000 nanometers, which can cover the BV particle size range. So in our experiment, we found that whereas Western blot has a detection limit of 10 to 9 particles per milliliter, flow nanoanalyzer achieve a detection limit of 10 to the 5 particles per milliliters. Therefore, we use this sensitive platform as the BV detection techniques from our downstream application. Having established our detection platform, we further investigate BV biomarkers. Since LTA and LPS are well known as markers from the gram-positive and gram-negative bacteria, we analyze their presence on BV membranes. And super-resolution image microscopy confirmed that LPS and LTA localize to the surface of BV membrane. So that means they may be a useful BV marker. We further use a flow nanoanalyzer to confirm that the LPS and LTA are specifically expressed on the BV divided from gram-negative and gram-positive bacteria. The concentration of LPS and LTA positive UV in the circulation of germ-free mice was lower than that in normal mice. And importantly, we found that BV concentration significantly decreased gut microbial elimination with antibiotic. This confirmed that these LPS and LTA are good biomarker for BV, and further confirmed that this EV are secret from the gut bacteria. To investigate the potential of the BV as indicator of intestinal disease, and we induce colitis in mice by this as gavage. The results show that after the intestinal barrier function decrease, LPS and LTA positive BEV increase in the blood circulation. And in vitro experiments also demonstrate that BEV can pass through the intestinal barrier. And next, we investigate the distribution of BEV in the circulation of healthy individuals. We observed that the circulating BEV increased with age, which correlate with the age-related rise in intestinal permeability. We also investigate BEV dynamic in patients with colitis and colorectal cancer. We found that circulating BEV levels are significantly evaluated in both colitis and in colorectal cancer patients and correlate with disease severity and tumor stage. That means they may potential good biomarkers for this gastro disease. In addition to the fluorescent antibody labeling, we also want to find whether there are better label techniques. So we develop antibiotic-based labeling method also. We use the polymyxin B label FITC pump polymyxins, which we know as antibiotic. We found that they can specifically label BEV derived from the gram-negative bacteria. We then established a mouse model of pneumonia infections enable serum EV with this plump. Interestingly, increase in circulating BEV preceded positive bacterial cultures and increase in conventional inflammatory markers, suggesting that circulating BEV may serve as early biomarkers of gram-negative bacterial infection. In our clinical validation, and we collect serum from healthy individuals, a patient with bacterial infections with bloodstream involvement and patient with bloodstream infections to measure the level of this BEV. We found that the BE levels correlate with infection severity, and moreover, BEV demonstrates strong diagnostic performance for BEV bloodstream infection, achieving an AUC of 0.947. And we also investigate the distribution of the pattern of BEV in serum and plasma sample. We are also interested in the distribution in the fecal samples because it directly reflects this bacteria EV secretion by the gut bacteria. Therefore, we develop a standardized protocol to isolate a fecal EV and conduct methodological comparison. Our results show that for density gradient and centrifugation, using herpes buffer in a top-down mode for 7 hours yield the highest BEV concentration. For size exclusion chromatography with a gel in a 20 milliliter column, BEV are most enriched infection 4 to 7. Further analyze revealed that combining density gradient centrifugation with a size exclusion chromatography using a 7-hour separation yield the highest purity of fecal BEV. Based on this technique basis, we analyzed the 16S ribosome RNA of fecal bacteria and BEV in the healthy individuals. And we found that a patient with precancerous tissue and colorectal cancer at Bible stage. And we found that the type and the relative abundance of intestinal bacteria of BEV show dynamic change under different colorectal disease stage. And we then analyzed the top 21 influential BEV genera based on the random forest model. The diagnostic AUC of intestinal BEV were also 0.78, indicating that the change in the type and the abundance of intestinal BEV are expected to be used for the colorectal cancer's diagnosis. And also, the above findings show that BEV are promising biomarkers for disease such as the infection disease and the cancer and other gastro disease. And they may also serve as promising marker for the age. We also we also want to find whether BEV can serve as a potential therapeutic carrier for different diseases. Because compared to other drug, they offer high drug loading efficiency, scalability for mass production, and ease of engineering and inheriting immunogenicity. And we found that we explore the therapeutic potential of BEV and preeclampsia. We found that the abundance of eclampsia mucinifera, a kind of probiotic, is reduced in pregnant women with preeclampsia and is negative correlate with hypertension. And this AKK AM is a gut probiotic. In the mouse model, we found that confirmed that this bacteria arose and found that the extragenous supplementation of AM can alleviate fetal growth restriction and improve placental structure damage in the mice with this disease. To investigate the effect of the AMEVs on PE mice, we administered AMEV by oral gavage and found that this EV can reduce blood pressure and proteinuria in the PE mice. And what's more, we found that AMEV can improve fetal growth restriction and placental structure damage in these mice. So in the in vitro cell line model, we investigate the effect of AMEV on trophoblasts and trophoblast cell function and find that the AMEV can promote the trophoblast proliferation and migration. And the above result indicated our work on preeclampsia in the context of inequalities. We conduct a preliminary investigation of another bacteria and Lactobacillus derived DV as a treatment of gastro disease. Okay, and in the mouse model, we found that this bacteria EV and can effectively alleviate the DSS-induced colitis. And at last, I would like to summarize our research. And first, we developed a flow nanoanalyzer with single particle detection precision, and for BEV detection in the complex real biological samples, including blood. And in addition to the commercial fluorescent antibiotic conjugate plumb from the specific level of OMV. And Clinically, we observed that the circulating BV level rise significantly during infection disease and when the intestinal barrier is compromised, indicating that BV may serve as early diagnostic biomarkers for colorectal cancer, colitis, and bacterial infection. And finally, in exploring therapeutic application, we found that BV from AM and other bacteria, they can hold promise for improving disease. And our team has offered a BV position paper, which provides a comprehensive review of BV types, contents, functions, and their roles in disease diagnostic and treatment. We invite everyone to read it, which has been published in the Interdisciplinary Medicine scientific journal. And last, I would like to take this opportunity to introduce this journal, Interdisciplinary Medicine. Short for IMED. IMED is co-founded by Nanfang Hospital of Southern Medical University and Wiley Publishing Group. And the Professor Lei Zheng is our editor-in-chief. And this journal published innovative medical and technical research using multidisciplinary approach and is supported by an international diverse editorial board. And our average time to first decision is 21 days, and there are currently no publication fees. We warmly welcome your submission. And yesterday we get the first impact factor. We get the first impact factor of this journal with 13.6. And also, I would like to introduce the Chinese Society for Extracellular, hosted by Nanfang Hospital of Southern Medical University. And this society has been successfully held at 8 annual meetings. We also established multiple work groups to advance the development of the EV field and create group standards to promote the EV standardization and application. We warmly welcome everyone to come to China and participate. And that's all about my presentation. And thank you very much.
Thank you very much, Dr. Bo Situ, for the insightful presentation. We truly appreciate you sharing your expertise. This is my summary of the first presentation. Bacterial extracellular vesicles are components of the bacteria, and it are formed by a lipid bilayer containing cytoplasmic proteins, nucleic acids, peptidoglycan, and virulence factors. Bacterial extracellular vesicles are important mediators of bacteria and participate in bacteria-host interactions. There are major challenges in being able to detect bacterial extracellular vesicles, such as lack of specific and universal BAV markers and lack of high-precision detection platform. Dr. Bo Situ's research aims to quantitatively detect these bacterial extracellular vesicles using a flow nanoanalyzer with very interesting results. Circulating bacterial extracellular vesicles increase with age, and it may serve as early markers of bacterial infections. In his presentation, he showed us two clinical situations where bacterial extracellular vesicles were increased as in patients with colorectal cancer and in preeclampsia, where the abundance Akkermansia muciniphila is reduced in pregnant women with preeclampsia and is negative correlated with hypertension. Now, let's move to our last lecture. It's my pleasure to introduce Dr. Yishuang Li. Dr. Yishuang Li, medical manager at Zybio Inc., PhD in dentistry from Osaka University, Japan. Specializes in bacterial pathogenesis and infectious disease using animal models. Manage multi-center clinical trials and contribute to clinical research at Osaka University Dental Hospital. Present at international conference with multiple first author publications. Bridges laboratory research, clinical practice, and medical industry innovation. Dr. Yishuang Li, please, you can sharing your presentation.
Thank you so much, Professor Carolina, for your warm introduction. Good morning and good evening, everyone. Thank you for joining today. And let me begin with a brief introduction of myself. My name is Yishuang Li. I currently work in the medical department at Zybio, where I focus on the infection. So today's seminar will center on the myxovirus resistance protein A, or in short, MXA. We will explore recent clinical evidence of MXA in several studies, especially we will focus on how MXA contributes to the diagnosis and management of viral infections. So let's begin. Here is our plan for today. First, we will talk about the current difficulties in the diagnosing infection. Next, I will introduce MXA as a novel host response biomarker for the viral infection. Then we will look at the recent clinical evidence. This includes both international and Chinese studies. Finally, we will discuss our findings and potential futures for MXA. Let's begin with the first section. We will look at the challenges in how we diagnose infections today. So antimicrobial resistance, or AMR, is a major threat we will talk about. A study published in The Lancet in 2019 showed the importance. In that year, AMR was linked to nearly 5 million deaths, 1.27 million of these cases were caused directly by the AMR. So infections in the lungs and the bloodstream are the most important factors here. So the AMR challenge is more than just a global problem. It's also obvious in certain regions like China. So here is a large outpatient study, and it found that antibiotics were given to the patients in about 11 over 50% of the antibiotic prescriptions were actually unnecessary, and only about 15% of them deemed suitable. So there is a big problem with people using too many antibiotics today. Look at some numbers from all over the world. Studies show that only half of all antibiotics are used correctly around the world. About 30% of outpatient antibiotic prescriptions in the US are not needed. The AMR grows because of this kind of misuse. 700,000 people die every year because of AMR. Now we know it is important to be able to tell the difference between bacterial infections and other types of infections, like viral infections, to make the prescriptions more accurate. This is a worldwide emergency. The tool we have now are a big part of the diagnostic challenge. A lot of traditional ways have their problems. For example, the microscopy can be time-consuming and subjective. The cultures are slow and may not be sensitive. And antibody and antigen tests have low sensitivity and window periods. And for an NAAT, it has contamination risk, and it's not practical for the low volume settings like the primary care clinics because they don't have enough patients. So we need better diagnostic tools as soon as possible. For example, some solutions are quick, accurate, cheap, and easy to use for the frontline settings. So how can we deal with these diagnostic problems? It's time to introduce MXA. The full name of MXA is myxovirus resistant protein A. It's a new biomarker for the viral host response. Let's take a quick look at the history of MXA research. It's been a long and fascinating journey. It all started in 1957 when Essex and Lindemann discovered the interferon. That was a great finding. Just a few years later, in the early 1960s, scientists found the MX gene in the mouse. MX gene is a gene linked to resistance against the virus. Then in 1979, Howler and his team made a key discovery. They found that MX gene product is exactly what enables interferon to terminate the virus inside the cells. That was a huge step in understanding how interferon works. From 1980s through the 2010s, scientists studied the entire MX protein family in different species. Among them, human MXA stood out. The role of MXA in our antiviral defense became more clear now. MXA is a key protein in our body's natural defense against the viruses. It's produced in a very specific way. Only type 1 and type 3 interferons can trigger its production. That's why MXA is called the ISGF, is short for interferon stimulated gene factor. So MXA is a large GTPase and with a molecular weight of 76 kilodaltons. One special feature is it can form oligomers on its own. This means it can link up with copies of itself to work against the virus. So how does MXA fight viruses? It targets the viral nucleocapsid directly. So in simple terms, it blocks the virus from assembling properly. As a result, the virus can't replicate or spread quickly. So why is MXA a biomarker for the viral infections? We need to know how it's induced. When a virus enters a cell, the cell releases the interferons. It's like a sounding alarm. These interferons then bind to a specific receptors on the nearby cells. The receptors on the cell surface are like the antennas. They receive the signal. Once the signal is received, it activates a protein called kinase. Kinase is like a switch. When the switch is turned on, it puts a phosphate group to the STAT proteins. And next, the STAT proteins form a complex called the ISGF3. This complex is like a signal carrier. It travels to the cell nucleus, where we know is a command center of the cell. In there, it's like a commander and turns on a group of genes. These are called the interference stimulated genes, or in short, ISGs. So the ISGs produce proteins that fight off virus directly. So one of the most important proteins is MXA. So that's why MXA is a strong indicator of viral infection. Let's look at now how MXA's expression changes over time. There are three important things here. First, it can only be made when the interferon is present. Interferon are definitely needed for MXA to be made. Because of this, MXA is a good way to tell when interferon signaling is active or not. And second, MXA works inside of the cells. It's a protein inside cells. So we can only find it in samples containing enough cells like PBMCs or the whole blood. It is not possible to measure MXA in the serum or plasma. Third, MXA starts working quickly. Just 1 or 2 hours after the interferon stimulation, it starts to rise. It takes about 16 hours to reach the highest level, and its half-life is more than 2 days. The right table shows MXA's response of common pathogens. As you can see, MXA level are usually rise during many acute viral infections. However, chronic viral infections like hepatitis B or C can suppress MXA's expression in the blood. This table shows a direct comparison between MXA and other common inflammatory markers. Look at IL-6, CRP, SAA, and PST. These markers usually rise during bacterial infections, but they can also go up during some viral infections. So this is difficult to tell the difference between bacterial and viral infections for these biomarkers. And now let's look at MXA. MXA tells a different story. It's highly specific. It doesn't increase during the typical bacterial infections, and instead, MXA only rises during the viral infections, which trigger an interferon response. This unique pattern makes MXA a reliable and accurate biomarker, and it can help doctors to differentiate between viral and bacterial infections. Then we would look at the clinical evidence. This part is all about how MXA can be used in the real world. We will start with international research. The first study comes from Finland and was published just last year. It focused on children with high fevers. The findings were impressive. MXA alone could clearly tell the difference between viral and bacterial infections, and the AUC was 0.96, and the MXA and CRP ratio reaches an AUC of 0.97. It's even better to the MXA alone. And this study enrolled all children came to the emergency room with severe fever, not just respiratory infections, and the blood samples were taken using a simple finger prick. So this shows MXA's potential in pediatric department, and it works really well, and it's easy to use even in very, very young children. Next one is a 2022 study from the US published in JAMA Network Open. It involved 20 outpatient settings across different regions. Let's now go back to Finland for a second study on children. This study focused on kids hospitalized with serious infections. The MXA-CRP ratio showed better performance to other markers. It had an AUC of 0.89, and better than the MXA alone, differentiating viral from the bacterial infections. And there were another important thing. The MXA could also tell the difference between true viral infections and harmless viral carriage. That helps avoid false positives and improves the diagnostic accuracy. And diagnosing infections was difficult during the COVID-19 pandemic. A 2020 UK study looked at the MXA and CRP in this context. The goal was to detect the COVID-19 in the hospitalized adults. The results were strong. The MXA-CRP combo showed 93% sensitivity and 86% of specificity. This suggests that during viral outbreaks, MXA and CRP can be an ideal tool for the hospital screening for infections. A recent UK study from last year gives us even more insight. It focused on real-world challenge, like multiple respiratory virus spreading at the same time, including influenza, SARS-CoV-2, and RSV. In this complex setting, the MXA RCRP test still works very well. It maintained a high MPV over 97% for all these three viruses. Importantly, it works well even when many patients were already vaccinated against COVID-19. So this shows MXA-CRP's value as a fast and reliable screening tool, especially in the crowded emergency rooms. It helps identify the causes of infection quickly and provide smart and effective use. MX may be used for it may be useful for more than just diagnosis. Recent research shows it might also help predict how severe COVID-19 will become. A Finnish study published in 2022 focused on the hospitalized COVID-19 patients. The findings were clear. High MX levels at admission were linked to more severe outcomes later. The patients need more breathing support using corticosteroids for longer than other patients and had lower blood oxygen levels. So what we can learn from this, high MX can reflect an early and intense interferon response to the virus. This could help identify patients at risk of getting worse right from the start. Here's an important question. Can MXs still work in people with weak immune systems? A 2023 study from Austria did research on that. Researchers look at the MX levels in PBMCs from the immunocompromised patients. The results were encouraging. There was a clear difference in MX between viral and bacterial infections, and the test had good diagnostic accuracy. More importantly, even immunosuppressive therapy didn't lower MX levels in the cells when the patients were infected by a virus. So that means MX is a strong and reliable biomarker, even in patients with weakened immunity. Now let's take a look at MX data from China. Our company Zybio had developed a rapid POCT kit for MXA. It was approved and launched in the Chinese market last year. Before then, we've started a series of clinical trials to gather more evidence on how well MXA works across the different conditions. Today, I will briefly introduce two key Chinese studies that shows the clinical value of MXA in the real-world settings. This year, the first adult study on the commercial kit of MXA in China was published. It focused on the sepsis patients, a group where infections are often hard to identify because they're complications. In these severe EO patients, quickly identifying the type of infection is crucial for timely and targeted treatment. CRP and PCT are widely used now, but they mainly respond to the bacterial infections. That makes it harder to detect viral infections in sepsis. So this study asked, could MXA help in this setting? The answer was promising. The MXA showed an AUC around 0.8, outperforming CRP and PCT alone in differentiating viral from the bacterial infections. And even better, when MXA was combined to CRP and the PCT, the accuracy improved to 0.847. This was quite good in these complicated cases. So in short, MXA showed real value in identifying the source of infection in severe EO adults and helps doctors to make fast and more accurate decisions. Now let's look at the multicenter study, which is still ongoing in China. This study is led by Professor Chao from the National Center of Respiratory Medicine. This manuscript is currently under submission. The goal is to evaluate how useful MXA is diagnosing both upper and lower respiratory infections. So far, 500 patients have been enrolled, and this study will provide important real-world evidence on how MXA supports the diagnosis and treatment of respiratory infections in the Chinese population. We've really come a long way. Let's bring everything together. In the final section, we will look at the clinical evidence of MXA so far, and we will explore where this promising biomarker might be headed in the future. Let's go over the clinical evidence of MXA and its many potential uses. First, MXA enables rapid and accurate diagnosis of viral infections. It detects interferon-mediated response early and making it useful in the primary care, emergency rooms, and outpatient settings. And unlike other markers, MXA is focusing on finding final infections from other ones. Second, MXA improved antibiotic stewardship by identifying viral infection more accurately. It helps to reduce unnecessary antibiotic prescriptions, which directly supports the fight against AMR. Third, MXA works well across the diverse patient groups. It's good in children and can help to differentiate true illness from the silent viral carriage. And it also works in adults, including those weakened immune systems, even in situations with multiple respiratory virus circulating outside. MXA remains reliable. And lastly, MXA supports better triage and source allocation. It helps doctors make faster, more informed decisions. It may also help to tell how severe the disease will be, such as in COVID-19, maybe could finding treatment and maybe could getting treatment strategies here. Let's now look at how MXA can be moved forward. Current limitations and research needs are still here. First, MXA level don't always rise in all kinds of viral infections. For example, in some chronic viral infections. And we need to explore more different types of infections and non-respiratory syndromes. And also, cost-effectiveness studies are also key for the wider clinical adoption. And moreover, it's also promising in monitoring responses to antiviral therapy, enabling more targeted use of these drugs. So what do we stand? Where do we stand? MXA is a validated and highly promising host response biomarker for the viral infections. The strong clinical evidence we reviewed today clearly supports its role, and it's good at distinguishing between viral and bacterial infections. In the end, MXA has the potential to make infection management better and fight against AMR. That concludes my presentation. Thank you very much for your time and attention today. Thank you very much.
Thank you very much, Dr. Yishuang Li, for your invaluable insights into this topic and this summary of the second presentation. Currently, bacterial resistance remains a challenge, so it is important to seek diagnostic tools that differentiate between bacterial and viral infections and detect them as quickly as possible. This is why this new test has emerged. Myxovirus resistant protein A. Myxovirus resistant protein A is a key innate antiviral protein. His antiviral mechanisms such as primarily targets and interacts with viral nucleocapsid proteins and disrupt viral nucleocapsid assembly, inhibiting viral replication and spread. The production of this protein is controlled by interferons. Measurement of this protein requires intracellular proteins from whole blood or peripheral blood mononuclear cells. This protein allows early identification of interferon-mediated viral etiology in diverse settings, primary care, ED, outpatients, and can differentiate between viral and bacterial infections, leading to a reduction in unnecessary antibiotic use because it accurately identifies viral etiology. In this presentation, Dr. Yishuang Li demonstrated the usefulness of this protein in pediatric, adult, immunocompromised, and ICU patients. It's important to mention that it still requires further research, but it turns out to be a promising biomarker for viral infections. Thank you, Dr. Yushan Lee. All right, everyone. We are now opening for Q&A. Please type your questions into the chat box and our speaker will address them live. Let's foster a collaborated exchange of ideas. Well, first question for Dr. Bo Situ. Today, Dr. Situ introduced some new research progress and potential application of bacterial extracellular vesicles obtained by their group. We've known that from fundamental research to final products, which can be used for therapy or clinical diagnosis, is a long process. Therefore, the first question to Dr. Situ, in China, what role do hospital or research institutions play in development of clinical applications products from cutting-edge technologies? Are there collaborations between hospital and enterprises? If so, what are the main forms of such collaborations?
Okay, thank you for your good questions. And in China, hospital and research institution play a crucial role in the development of clinical application product from cutting-edge technologies, mainly in the following aspect. And first, providing clinical needs and data support. And hospitals can identify practical needs from clinical practice, guiding the direction of technical R&D. Meanwhile, they provide important basis for product development through accumulated case data and sample. And secondly, conducting clinical trials and verification. And research institution and hospital can carry out clinical trials on developed clinical application product to test their safety and efficacy, ensuring that product meet the clinical application standards. And thirdly, promoting technical innovation and transformation. With the professional scientific research capabilities, and hospital and research institution can work together with the R&D teams to overcome the technical challenge, accelerating the transformation of the cutting-edge technologies into clinical application. And there is extensive collaboration between the hospital and the enterprises, with the main forms as follow. And first, jointly build the R&D platforms. Hospital and enterprise establish R&D laboratories or research centers to collaborate, integrating resources from both sides to jointly carry out the R&D of clinical application products. And secondly, project cooperation and development. For specific clinical needs or technical projects, enterprise and hospital sign cooperation agreement, clarifying their respective responsibilities and divisions of labor to collaboratively promote the R&D, testing, and industrialization of the project. And thirdly is the technological transfer and licensing. And hospital or research institution transfer develop technical achievement to the enterprise, which attain the right to use and commercially develop the technology for product production and sales. And the fourth point is the talent exchange and training. And both sides carry out talent exchange activities, and enterprises provide practical opportunities and technical training for hospital researchers, and while hospital offer clinical knowledge and experience guiding to enterprise R&D personnel, promoting the integration and development of industry university research talent. And that's all of my answer. Thank you very much.
Thank you, Dr. Situ. The second question for Dr. Lee. The report highlights that the mysovirus resistant protein A, NSI, CRP combination has demonstrated excellent performance in multiple studies. AUC 0.89 and 0.97. However, data from China show that antibiotic overuse remains prevalent in 51.4%. Inappropriate use. My question is, from evidence-based research to clinical practice, what factors are hindering the widespread adoption of MSI? Have multi-center studies in China revealed any region or population-specific DERSOL requirements?
Okay, thank you for your wonderful question. So let's from the first one. I think compared to the well-known infection mechanisms like CRP and PCT, which have been used in clinical settings for decades, MX is still very, very new. Commercial MX tests can have only been available for less than 3 years worldwide, I think. Although MX shows excellent performance in the studies, many doctors I interviewed are still unfamiliar with it. And I think clinical awareness takes time to build, so we still have a long way to go. And as for the population-specific thresholds, the evidence in this time point is quite limited. I think there are several companies worldwide produce the MX commercial tests, but each of them uses different manufacturing methods, which lead into the variation in test results. So although we didn't observe huge differences between the studies from different countries right now, our company's product currently only has data from Chinese studies at this time point. So we hope to do more clinical trials in other countries and to better understand the regional or the population-specific thresholds in the future. And thank you very much for a wonderful question. I hope I made myself clear. Thank you.
Thank you, Dr. Lee. I would like to extend our deepest gratitude and appreciation to both of our distinguished experts. It has also been a distinct honor for me personally to participate in and facilitate this important meeting. Engaging with such high caliber discussion and learning from both of you has been incredibly rewarding. Thank you all for your participation.
Thank you. Thank you, Professor Colin Neguchi Espinoza, Professor Guo Tu, and Dr. Yixuan Li. As we conclude the third session of the DiagHub series, we would like to once again extend our sincere gratitude to our two distinguished speakers for their insightful presentations, and to our moderator for guiding the session so smoothly. With 3 successful sessions now behind us, DiagHub has continued to expand its reach and has received overwhelmingly positive feedback from the global diagnostics community. We are truly grateful for your continued support and engagement. Our team remains committed to bringing you more high-level academic discussions and more meaningful exchanges in the field of diagnostics. Stay tuned for our next session, which will focus on clinical laboratory medicine. We look forward to seeing you again. Thank you. Goodbye today.
Bye today.